Far beyond Neptune, something massive may be hiding in total darkness, tugging on worlds it has never let us see. For 30 years, one hidden world has bent the orbits of icy objects at the edge of our solar system, and we are only now catching its shadow. You are about to meet a scientist who found a lonely red world where nothing should exist, a wall of empty space that breaks the rules of physics, and a telescope catching heat from something we cannot photograph. What if the ninth planet was never lost, but simply waiting? Every planet we know sits close to the Sun, but past Neptune, 12 icy worlds line up in a way that should be impossible by chance. If you're enjoying this journey into the unknown, hit subscribe, because tonight's mystery gets stranger with every chapter. Something out there is real, and it is watching the edge of everything we know. Prepare yourselves. We begin. A red dot crawled across a computer screen in California, and nobody in the room understood what they were looking at. It was late 2003. Astronomer Michael Brown had spent years scanning the sky for frozen worlds beyond Pluto, and he had found plenty. But this one moved differently. Most distant objects crept slowly across the frame, night after night, tracing a smooth and predictable path. This one barely moved at all. Brown checked the numbers twice, then a third time. The object was so far away that its motion against the stars had almost vanished. He named it Sedna, after an Inuit goddess who was said to live in the frozen depths of the ocean. The name fit. Sedna's orbit dragged it out to nearly 600 billion miles from the Sun, distances so extreme that sunlight there would feel like starlight, faint and cold. But the real shock came later, when Brown ran the math on Sedna's full orbit. At its closest approach, Sedna still stayed roughly 7 billion miles from the Sun, about 80 times farther than Earth. At its farthest point, it stretched out to nearly 90 times that distance again. One full lap around the Sun takes Sedna about 11,000 years. For comparison, that is longer than all of recorded human history, repeated twice. Here is the part that broke the model. Every object in the solar system that we understood followed a rule. Objects close to the Sun feel a strong gravitational pull and swing around quickly. Objects farther out feel the pull of larger planets like Neptune, which yank and bend their orbits into predictable shapes. Sedna orbits so far away that Neptune's gravity barely touches it. Nothing should have shaped its strange, stretched path. Nothing that we could see. Astronomers began asking a question that still has no clean answer. If no known planet pulled Sedna into this orbit, what did? A distant star during the Sun's youth, a passing rogue world, or something still out there, quietly orbiting in the dark, tugging on Sedna the same way it apparently always had? Brown himself was stunned by the implications. Sedna's discovery hinted that the outer solar system was not empty and simple, the way textbooks described it. It suggested a hidden structure, shaped by something we had never detected, a gap in our map of the solar system, and possibly a gap in our understanding of what actually lives inside it. For years, Sedna sat alone in the record books, a lonely oddity that nobody could fully explain. Scientists filed it away as a mystery worth revisiting once better telescopes came online. What they could not have guessed is that Sedna was not alone at all. It was the first thread of a pattern that would take another decade to fully reveal itself. One small, cold clue pointing towards something enormous. The story of Sedna is confirmed. Its extreme orbit is real, its distance measured and verified. What remains a mystery is the cause behind it, a question that would soon get far stranger and far more urgent. Picture the solar system as a marching band on a football field, every planet moving in step, roughly the same flat plane, roughly circular paths, all following the same simple rhythm set by the Sun's gravity. That is the tidy picture most people grow up with. Sedna shattered it. To understand why Sedna's orbit is so troubling, you need to understand how normal orbits form. When the solar system was young, a swirling disk of gas and dust surrounded the Sun. Planets formed inside that disk, and their gravity nudged smaller objects into relatively neat, flattened orbits. Objects close to the Sun move fast and tight. Objects farther out, like Neptune, still get bent and shaped by the gravity of the giant planets nearby. Every known object has some explanation for why it moves the way it does. Sedna breaks the pattern completely. Its closest approach to the Sun is so distant that Neptune's gravity, the shaping hand behind most trans-Neptunian objects, simply cannot reach it. Neptune's pull weakens dramatically with distance, following a rule where the force drops off with the square of that distance. Push an object twice as far away, and the pull is 4 times weaker. Push it 80 times farther, and the pull becomes almost nothing. Yet somehow, something bent Sedna's path into this extreme, elongated shape. Something reached across billions of miles of empty space and left a fingerprint that scientists still cannot explain. 3 explanations exist, and each one is stranger than the last. The first is that a passing star, billions of years ago when the Sun was newly formed and crowded among other young stars in its birth cluster, swung close enough to yank Sedna into its current shape. The second is that Sedna was never born in our solar system at all, and was captured from another star system entirely during a close encounter in the deep past. The third explanation is the one that refuses to go away, a planet-sized object orbiting far beyond Neptune, still tugging on distant worlds today. The first 2 explanations share a weakness. They both describe one-time events from billions of years ago, leaving no ongoing effect. But scientists studying the outer solar system did not find one strange orbit. They found several, all echoing the same unexplained pattern, as if something was still out there shaping them right now in real time. Sedna alone might have been dismissed as a cosmic coincidence, a fluke from the solar system's chaotic youth. But nature rarely repeats a coincidence by accident. When a second, lonely, distant world turned up years later, tracing an eerily similar path, the coincidence started to look like a signal. And once scientists began searching harder for objects like Sedna, they discovered something even more disturbing waiting in the data. Space is not supposed to have walls. There is no fence out past Neptune, no barrier holding objects back from certain distances. And yet, when astronomers mapped out the region beyond the Kuiper belt, they found exactly that. A gap, a stretch of space between about 50 and 75 times Earth's distance from the Sun where almost nothing exists. Scientists call it the Kuiper Cliff, and the name captures the shock of discovering it. Imagine driving down a road lined with houses on either side, then suddenly hitting a stretch with nothing at all, followed by a completely different neighborhood far beyond it. That is what this region of space looks like. Objects are common inside the main Kuiper belt. Then, abruptly, the population plummets. Then, far beyond that emptiness, Sedna and its strange cousins reappear, orbiting alone in the deep dark. At first, astronomers assumed this gap was simply a blind spot, a limitation of their telescopes rather than a real feature of space. Faint, small objects that far away are brutally hard to detect. Maybe the gap was full of icy worlds we simply could not see yet. But the more astronomers searched, using increasingly powerful surveys, the more the gap held its shape. It was not a trick of faint light. It appeared to be a real structural feature of the solar system, a boundary that formed for a reason nobody could fully explain. One leading idea connects directly back to a hidden planet. If a massive object orbits far beyond this gap, its gravity could have swept the region clean over billions of years, flinging smaller objects either inward toward the Kuiper belt or outward into the deep distances where Sedna now lives. Gravity, over enough time, works like a broom, and a large enough broom leaves a very clean floor behind it. This idea carries real weight because we have already seen something similar happen inside our solar system. Jupiter's gravity clears gaps in the asteroid belt, regions where no asteroids survive because Jupiter's pull destabilizes anything that drifts there. If a planet-sized object exists far beyond Neptune, it could be doing precisely the same thing on a much larger, much colder scale, one that stretches across billions of miles of frozen darkness. The Kuiper cliff remains one of the most quietly unsettling puzzles in the outer solar system. It is confirmed, mapped, and real. What caused it is still an open question. One more piece of evidence stacking up in a growing case. And the next piece would not stay hidden for long, because in 2014, astronomers stumbled onto an object that made the pattern impossible to ignore. A decade after Sedna's discovery, two astronomers, Chad Trujillo and Scott Shepard, spotted a faint object crawling through their survey images. It was smaller than Sedna, roughly half its size, maybe 400 miles across, small enough to lose in the glare of a single bright star. They nicknamed it Biden, a nod to a sitting vice president, before giving it the formal name 2012 VP 113. At first glance, this looked like a nice but minor discovery. One more icy body added to a long list. Then they calculated its orbit, and the room went quiet. 2012 VP 113 traced an orbit strikingly similar to Sedna's. Its closest approach to the Sun sat at roughly 80 times Earth's distance, almost exactly matching where Sedna's own closest approach occurs. Two objects, discovered a decade apart in completely different parts of the sky, both stopping their inward journey at nearly the identical distance. If this were random chance, the odds would be staggeringly unlikely. Orbits in the outer solar system can point in almost any direction, tilt at almost any angle, and stretch to almost any length. For two independent objects to land on nearly matching closest approaches by pure coincidence would be like two strangers, blindfolded, throwing darts from across a football field and both hitting the same square inch of the board. Trujillo described these two objects as just the tip of the iceberg. He suspected far more were waiting to be found, all echoing the same unexplained alignment. He was right. Over the following years, astronomers kept finding more, object after object, each one adding another data point to a pattern that refused to look accidental. The scientific term for what they measured is called the argument of perihelion, a technical way of describing the direction an orbit points at its closest approach to the Sun. For Sedna, 2012 VP 113, and the objects that followed, this direction kept clustering around the same narrow range again and again. Picture a room full of clock hands, each one representing an orbit. In a random solar system, those hands would point in every direction, scattered like spilled matchsticks. Instead, these particular hands kept pointing roughly the same way, like something invisible was quietly nudging them all into formation. Shepard and Trujillo proposed the explanation that would eventually reshape the entire field. A large planet, they suggested, roughly 2 to 10 times the mass of Earth, orbiting hundreds of times farther from the Sun than we do, could be shepherding these smaller, icier worlds into synchronized alignment through gravity alone. It was a bold claim built on just two objects. Skeptics were quick to point out that two data points do not make a pattern. They make a coincidence waiting for an explanation. But 2 years later, a much larger team would take this same idea, expand it to a full population of distant worlds, and turn a curious anomaly into one of the most compelling mysteries in modern astronomy. By the middle of the 2010s, astronomers had assembled a small but growing collection of extreme trans-Neptunian objects, distant icy worlds whose orbits stretched far beyond Neptune's reach. Individually, each one was a curiosity. Together, they became something far more disturbing. Two astronomers at Caltech, Konstantin Batygin and Mike Brown, the same Brown who discovered Sedna over a decade earlier, decided to look at the full picture rather than one object at a time. They gathered data on 6 of these extreme objects, including Sedna and 2012 VP 113, and plotted their orbital directions on a single chart. What they found made their hands shake. All 6 orbits clustered together, pointing in nearly the same direction through space, like 6 arrows fired from wildly different locations, somehow landing in the same small target. Not only did their closest approaches point the same way, their orbital planes tilted at similar angles too, as if something had physically pushed all 6 objects into a shared formation. Batygin and Brown ran the numbers on how likely this clustering was to happen purely by chance. The answer stunned them, roughly 0.007%. To put that in perspective, imagine buying a single lottery ticket and somehow winning first place 14 times in a row. That is how unlikely random chance made this arrangement look. Skeptical scientists immediately raised a fair question. Telescopes do not scan the whole sky evenly. Some regions get searched more carefully than others, based on where astronomers happen to be looking during any given survey. Could this clustering simply reflect where we searched, rather than something real happening in space? It is a serious concern, one astronomers take seriously in every field of research. But when Brown and a colleague later built detailed models correcting for exactly this kind of observational bias, the clustering held firm. Even after accounting for where telescopes had and had not searched, the alignment remained statistically striking, far beyond what randomness alone would produce. 6 objects should not agree on anything by accident, not their distance, not their direction, not their tilt. Something out there was apparently organizing them, the same way a magnet organizes iron filings scattered across a table into smooth, curving lines. No visible hand does the work, yet the pattern snaps into place regardless. Batygin and Brown proposed the explanation that would soon dominate headlines around the world: a single massive planet, orbiting far beyond Neptune, its gravity powerful enough to slowly herd these 6 distant worlds into synchronized alignment over millions of years. They gave this hypothetical world a name that stuck instantly in the public imagination: Planet 9. And unlike vague speculation from decades earlier, this time the scientists came prepared with real numbers, a real orbit, and a real prediction for where a search might actually find it. Gravity is not gentle at these distances, but it is patient. To understand how a hidden planet could organize 6 separate worlds without ever touching them, it helps to picture something closer to home. Watch a sheepdog work a flock of sheep. The dog never grabs a single sheep directly. Instead, it moves along the edges, applying gentle, repeated pressure, and slowly the entire flock drifts into a tight, organized group. A massive planet does something remarkably similar to smaller objects nearby, except its tool is gravity instead of barking and darting movement, and its timescale is millions of years instead of minutes. Here is how the process works. When a large planet orbits at a steep tilt and a stretched, elongated path, its gravity does not pull evenly on everything around it. Instead, it applies stronger tugs at certain points in its orbit and weaker ones at others. Over enough time, this repeated, uneven tugging nudges nearby smaller objects into orbits that share certain traits with the planet doing the shepherding, particularly their orientation and tilt. This is not a wild or radical idea. Astronomers have already watched shepherding happen inside our own solar system on a much smaller scale. Saturn's rings contain tiny moons called shepherd moons, and their gravity keeps the icy particles in Saturn's rings confined into narrow, well-defined bands, instead of drifting apart into a chaotic disk. Remove those tiny moons, and the rings would slowly spread out and lose their sharp structure. Planet 9, if it exists, would essentially be playing shepherd moon on a solar system scale, its gravity reaching across hundreds of times the distance from the Sun to Earth, gently guiding icy Kuiper belt worlds into synchronized alignment over unimaginable stretches of time. The math behind this idea is not simple guesswork. Batygin and Brown built detailed computer simulations, placing a hypothetical planet of a certain mass at a certain distance on a certain tilted orbit, then letting the simulation run forward across millions of simulated years. When they tuned the planet's properties correctly, the simulation reproduced the exact clustering pattern seen in the real Kuiper belt objects, almost perfectly. That result mattered enormously. It meant this was not just an interesting coincidence dressed up with a dramatic name. A real physical mechanism could explain the pattern, tested and modeled with the same tools astronomers use to track spacecraft and predict eclipses. Still, a working simulation only proves that an explanation is possible, not that it is true. Other explanations remained on the table, but the shepherding model gave scientists their first solid, testable target: a real planet with a predicted size, a predicted distance, and a predicted stretch of sky where it might be hiding right now. In January of 2016, Konstantin Batygin and Mike Brown published their findings in a respected scientific journal, and the response was immediate and enormous. Newspapers around the world ran headlines suggesting a real ninth planet had finally been found. That was not quite accurate. Nobody had seen this planet directly. What Batygin and Brown had actually done was something almost as remarkable. They had built a mathematical case so compelling that the entire astronomical community felt obligated to take it seriously. Brown was no stranger to controversy involving planets. Years earlier, his discovery of the dwarf planet Eris had helped trigger the decision to reclassify Pluto, stripping it of full planet status. Brown even earned the nickname Pluto Killer for his role in that debate. Now, ironically, he found himself building the case for an entirely new planet to take Pluto's old place in the solar system's lineup. Their paper laid out a specific, testable prediction: a planet with somewhere between 5 and 20 times the mass of Earth, an orbit stretching between roughly 400 and 1,000 times Earth's distance from the Sun, a steep, tilted path unlike anything the 8 familiar planets follow. This was not vague speculation. It was a target with real coordinates, real physical boundaries, something telescopes could actually search for. The scientific community split almost immediately into two camps. Excited researchers began refining the model, running their own simulations, and searching archived telescope data for any sign of a match. Skeptical researchers raised the observational bias question again and pushed back hard on how confident anyone should be based on just 6 oddly aligned objects. Both camps had valid points. Science does not settle disputes through excitement or through skepticism alone. It settles them through evidence, and at that stage, the evidence pointed towards something real without providing the one thing that would end all argument: an actual photograph of the planet itself. What made this moment different from earlier planet hunting mysteries throughout history was the sheer weight of mathematics behind it. Batygin and Brown were not simply noticing an interesting pattern and speculating about causes. They had built and tested a specific physical model, one that could be checked, challenged, refined, and potentially disproven by future data. That kind of rigor is exactly what separates a wild guess from a genuine scientific hypothesis. And history offered an eerie parallel that made many astronomers take the idea even more seriously. Because this would not be the first time a strange gravitational pattern in the solar system led directly to the discovery of a real, previously unknown planet, hiding in plain sight the entire time. If Planet 9 is real, it is unlike any planet humans have ever laid eyes on. To picture it clearly, start with size. Batygin and Brown's calculations suggest a mass somewhere between 5 and 10 times that of Earth, possibly larger. That places it in a category scientists call a sub-Neptune, smaller than ice giants like Uranus or Neptune, but many times heavier than our own rocky home. Now, stretch your imagination across distance, because this is where things become almost impossible to picture using everyday comparisons. Earth orbits the Sun at a distance of about 93 million miles, a distance scientists shorthand as 1 astronomical unit. Neptune, the most distant known planet, orbits at about 30 times that distance. Planet 9's predicted orbit stretches out to roughly 700 times that distance, drifting as far as 600 times farther from the Sun than Earth itself. If the solar system were shrunk down so that Earth's orbit fit inside a school gymnasium, Neptune would sit somewhere in the parking lot outside. Planet 9, at these predicted distances, would be somewhere in a different city entirely. This distance explains almost everything about why the planet remains so difficult to find. Sunlight fades dramatically with distance, following a mathematical rule where brightness drops off with the square of that distance. Push an object twice as far from the sun, and it receives only a quarter of the light. Push it 600 times farther, and the sunlight reaching it becomes almost unimaginably faint, a dim twilight compared to the blazing daylight we experience on Earth. That faintness works both ways. Just as little sunlight reaches Planet 9, almost none of that light reflects back toward Earth for our telescopes to detect. Predicted brightness estimates place this planet at the very edge of what even our most powerful ground-based telescopes can currently detect, buried among millions of background stars in deep space photographs. The orbit itself adds another layer of difficulty. Unlike the nearly circular paths most planets follow, Planet 9's predicted orbit is steeply elongated and tilted at a dramatic angle compared to the flat plane where the 8 familiar planets travel. One full trip around the Sun would take somewhere between 10,000 and 20,000 years, meaning the planet has barely budged from its position since before the invention of writing. All of this paints a portrait of a world defined almost entirely by absence. Absence of light, absence of warmth, absence, so far, of direct confirmation. And yet its predicted gravitational fingerprint keeps showing up, again and again, in the orbits of the smaller worlds scattered around it, worlds that continue behaving exactly as this invisible giant would demand. Searching for Planet 9 is not like searching for a needle in a haystack. It is closer to searching for one specific grain of sand somewhere across an entire beach at night, using a flashlight with a narrow beam. The core problem comes down to two brutal facts working together. Planet 9 sits extraordinarily far away, and it likely reflects very little sunlight back toward Earth. Even with humanity's most advanced telescopes, an object this dim, this distant, blends almost seamlessly into a background sky, packed with billions of stars and galaxies. Telescopes searching for objects like this typically photograph the same patch of sky multiple times across several nights. Stars stay fixed in place from photo to photo, but objects within our own solar system slowly shift position as they orbit. Software compares these images, hunting for anything that moves. It sounds simple. In practice, it is staggeringly difficult. At Planet 9's predicted distance, its motion across the sky each night would be almost imperceptibly small, buried beneath a wall of noise from the telescope equipment itself, the atmosphere, and the sheer number of background objects cluttering every image. A fast-moving nearby object stands out easily. A nearly motionless object at the edge of detectability looks almost identical to a distant star or a flaw in the camera sensor. Then there is the sheer size of the search area itself. Even though Batygin and Brown's calculations narrowed down a rough region of sky where Planet 9 likely sits, that region remains enormous, far larger than any single telescope can photograph in one session. Searching it thoroughly means scanning patch after patch, night after night, across years of dedicated observing time, competing with countless other research priorities for scarce telescope access. Some astronomers compare the challenge to searching for a specific person somewhere across the entire population of a mid-sized country, using only a security camera that captures one grainy photograph per night. You might eventually spot them, but only with enormous patience, enormous luck, or a dramatically better camera than anything currently available. This difficulty explains why, despite a full decade of searching since Batygin and Brown's original prediction, no confirmed direct detection has emerged. It is not evidence against Planet 9's existence. It reflects the genuine, staggering difficulty of the search itself. But astronomers are not simply waiting around for luck to strike. New tools, new telescopes, and entirely new detection strategies have emerged in recent years, each one chipping away at the odds. And buried in old, previously unexamined data, one particular tool would soon offer the most tantalizing clue yet, hiding in plain sight for decades before anyone thought to look at it the right way. Return for a moment to that strange gap in the outer solar system, the region where the population of icy worlds abruptly collapses to almost nothing. Scientists have studied the Kuiper cliff for years, and the deeper they dig, the stranger it becomes. Picture the Kuiper belt as a crowded highway of icy traffic, thick with vehicles moving at every possible speed, from roughly 30 to 50 times Earth's distance from the Sun. Then, at that 50 mark, the highway seems to simply end. No gradual thinning out, no slow fade into emptiness, just a sudden, sharp cutoff, followed by open road for millions of miles before Sedna and its lonely cousins reappear far beyond. Astronomers initially assumed this cliff might simply reflect the limits of their equipment, a region too faint and too distant to properly survey with the telescopes available at the time. But newer, far more sensitive surveys have continued to confirm the same basic pattern. The cliff appears real, not just an illusion created by weak technology. If the cliff is genuine, something must explain it, and the two leading candidates circle back to familiar suspects. The first possibility involves the earliest chapter of the solar system's history, when the giant planets were still migrating through their orbits, scattering debris and reshaping the entire outer solar system before eventually settling into the stable arrangement we see today. This chaotic early period could have swept the region clean, leaving the cliff as an ancient scar from billions of years ago. The second possibility points once again toward a hidden planet. If a massive object orbits beyond this gap, its gravity could actively prevent smaller objects from settling into this particular distance range, continuously clearing the region the same way a lawnmower keeps a strip of grass permanently short, no matter how often new grass tries to grow back. Distinguishing between these two explanations matters enormously because they tell two completely different stories about our solar system. One describes a scar from ancient chaos, healed over and now inactive. The other describes an ongoing, active process, shaped by something still out there today, still exerting its influence on the world right now, in the present moment. Recent survey data has started leaning toward the second, more unsettling explanation. The cliff's edge appears remarkably sharp and well-defined, more consistent with active, ongoing gravitational clearing than with a fading memory from billions of years in the past. If that interpretation holds, the Kuiper cliff becomes something far more significant than a strange gap in a map. It becomes a footprint, a trace left behind by something massive, patient, and currently in motion through the darkest edges of our solar system. Long before Sedna, before the Kuiper belt was even discovered, astronomers faced a nearly identical mystery involving a planet we already knew. In the early 1800s, astronomers tracking Uranus noticed something was wrong. The planet kept drifting slightly off course, refusing to follow the smooth, predictable path that Newton's laws of gravity demanded. At first, scientists assumed they had simply made small errors in their calculations or their telescope measurements. But the discrepancy persisted, showing up again and again across years of careful observation. Uranus was being pulled by something, some gravitational influence that nobody could directly see or explain. Two mathematicians, working independently in France and England, tackled the problem using nothing but pen, paper, and Newton's equations of gravity. If an unknown planet existed beyond Uranus, they reasoned, its gravity could explain the wobble perfectly. Using nothing more than careful calculation, they predicted almost exactly where this hidden planet should be sitting in the night sky. In 1846, astronomers pointed a telescope at the precise coordinates these calculations predicted. Within hours, they found it. Neptune, a real planet, sitting almost exactly where pure mathematics had said it must be, discovered not by accident, but by prediction. This moment remains one of the most celebrated triumphs in the history of astronomy, proof that gravity's invisible fingerprints can reveal objects long before anyone manages to see them directly. Uranus's wobble was the clue. Neptune was the answer hiding behind it. The parallel to Planet 9 is almost impossible to ignore. Once again, astronomers are studying strange, unexplained deviations, this time in the orbits of distant, icy worlds rather than a full-sized planet. Once again, mathematics points toward a hidden mass, exerting influence from somewhere still unseen. Once again, a specific search region has been calculated using nothing but the gravitational fingerprints left behind on smaller, already discovered objects. History does not repeat itself exactly, and scientists are careful not to treat this parallel as guaranteed proof. Plenty of gravitational mysteries throughout history turned out to have far more mundane explanations, unrelated to any hidden planet at all. But the Neptune story demonstrates something important. Sometimes, the universe really does hide massive objects in plain sight, revealing them only through the subtle gravitational traces they leave behind on everything nearby. For scientists chasing Planet 9 today, Neptune's discovery serves as both inspiration and a cautionary reminder. Inspiration, because it proves this exact method has worked before, spectacularly. A cautionary reminder, because for every triumphant story like Neptune's, history also holds a far more famous cautionary tale, one involving a hidden planet that mathematics predicted with total confidence, and that turned out to never exist at all. The story of Neptune's discovery deserves a closer look, because the details reveal exactly how powerful and exactly how demanding this method of planet hunting truly is. After Uranus was discovered in 1781, astronomers spent decades carefully tracking its position, plotting its expected path using Newton's well-established laws of gravity. Everything worked perfectly, until it did not. By the 1830s, Uranus had drifted noticeably away from where calculations said it should be, arriving early in some parts of its orbit and lagging behind in others. A French mathematician named Urbain Le Verrier and an English mathematician named John Couch Adams each tackled the problem separately, unaware that the other was working on the exact same puzzle at the exact same time. Both men assumed the same explanation. An unknown, more distant planet was tugging on Uranus with its own gravity, creating the discrepancy. The math required was staggeringly complex for the era, performed entirely by hand, without calculators, without computers, using nothing but algebra, geometry, and enormous patience. Leverrier eventually sent his predicted coordinates to an astronomer in Berlin, urging him to check a specific patch of sky. That astronomer pointed his telescope toward the coordinates on the very night he received the letter. Within about 1 hour of searching, he spotted an object that did not match any star on his charts. It was Neptune, found less than 1 degree away from where the math had predicted it should be, an almost unbelievable level of precision considering the planet sits over 2.5 billion miles from Earth. This discovery proved something profound about how the universe works. Gravity leaves fingerprints. Even when an object cannot be seen directly, its pull on nearby objects creates ripples, small but measurable deviations that careful mathematics can trace back to their source. Modern astronomers chasing Planet 9 are essentially running this exact same playbook, updated with modern telescopes and modern computing power. Instead of tracking one planet's wobble, they are tracking the clustered orbits of multiple distant Kuiper belt objects. Instead of hand calculations stretching across years, they run detailed computer simulations capable of testing thousands of possible scenarios within days. The core logic remains identical across nearly 2 centuries. Look for unexplained gravitational effects. Calculate what kind of object could cause them. Predict where that object should be hiding. Then point a telescope at exactly that location and see what appears. It worked spectacularly for Neptune. Whether it will work again for Planet 9 remains the question driving telescopes and careers forward today. But history also offers a sharp warning, because this same method, applied with equal confidence just decades later, led astronomers down a path that would waste nearly a century chasing a planet that was never really there at all. Long after Neptune's triumphant discovery, astronomers noticed something odd. Even accounting for Neptune's gravity, Uranus still seemed to drift slightly off its predicted path. And Neptune itself, some argued, showed tiny irregularities of its own. Could yet another hidden planet be lurking even farther out? An American astronomer named Percival Lowell became convinced of exactly that. In the early 1900s, he devoted enormous time and money to searching for what he called Planet X, a hypothetical world he believed was tugging on both Uranus and Neptune from somewhere beyond them. He built his own observatory in Arizona specifically to hunt for it. Lowell died in 1916 without finding his planet, but 14 years later, an astronomer at his observatory named Clyde Tombaugh spotted a faint, slowly moving object exactly in the region Lowell had predicted. Astronomers celebrated. Planet X had apparently been found. They named it Pluto. For decades, Pluto held its place as the 9th planet in our solar system, taught in classrooms worldwide as proof that Lowell's calculations had succeeded, just as Leverrier's had for Neptune. Then, later analysis revealed an uncomfortable truth. Pluto was far too small and far too lightweight to produce the gravitational tugs Lowell had originally calculated. His math had been wrong. His predicted planet, strictly speaking, never actually existed. Pluto's discovery, it turned out, was closer to a fortunate accident than a triumph of precise calculation. A small, icy world that happened to be sitting near where Tombaugh was searching, unrelated to the wobble that originally sent Lowell hunting in the first place. Later, more accurate measurements of Neptune's mass revealed there had never been any real discrepancy needing an explanation at all. The mystery had been based on a measurement error from the start. This history matters enormously for how scientists approach Planet 9 today. It proves that gravitational anomalies can sometimes lead astronomers to real, undiscovered planets, exactly as it did with Neptune. But it also proves those same anomalies can sometimes be measurement errors, statistical flukes, or simple mistakes, exactly as it did with Lowell's original Planet X calculations. Modern researchers studying Planet 9 are keenly aware of this history, and it shapes how carefully they approach their own claim. Batygin and Brown have repeatedly emphasized that their hypothesis remains unconfirmed, a strong and testable prediction, not a discovery. They know full well what happened the last time astronomers grew too confident, too quickly, chasing a hidden world, using nothing but calculations and hope. Yet the differences between these historical cases matter just as much as their similarities. Lowell was working from a single planet's slight wobble, using an already outdated estimate of Neptune's mass. Batygin and Brown are working from 6 independent objects, each one confirmed through direct telescope observation, all pointing toward the same conclusion using modern, precisely measured data. Whether that distinction proves decisive remains to be seen, and not every scientist in the field is convinced. Not every astronomer believes Planet 9 is real, and their objections deserve serious attention rather than dismissal. Science advances fastest when its boldest claims face its sharpest challenges. The central skeptical argument centers on a concept called observational bias, and it deserves careful unpacking because it is genuinely subtle. Telescopes cannot scan the entire sky equally. Survey teams choose specific regions to search based on funding, based on available telescope time, based on which patches of sky are visible during a given season, and based on where previous searches already looked. This means our collection of known distant objects was never a random, unbiased sample of everything actually out there. A team of researchers, led by astronomer Corey Shankman, argued that this bias alone could fully explain the apparent clustering that so excited Batygin and Brown. If certain regions of sky simply received more thorough searching than others, any objects found there would naturally appear clustered, purely as an artifact of where astronomers happen to point their telescopes. with no hidden planet required at all. This is not a minor technical quibble. It strikes directly at the foundation of the entire Planet 9 hypothesis. If the clustering is simply a mirage created by uneven searching, then there is no mystery left to explain, and no hidden planet needed to explain it. Batty, Ginn, and Brown took this challenge seriously and spent years developing detailed statistical methods specifically designed to correct for exactly this kind of bias. They built models simulating how thoroughly different regions of sky had actually been searched, then tested whether the clustering still held up once that uneven searching was properly accounted for. Their corrected analysis concluded that the clustering remained statistically significant even after removing the bias, though notably less overwhelming than their original, uncorrected estimate, where their first calculation suggested only a tiny fraction of a % chance of random coincidence. Their bias-corrected analysis still found only a small handful of % chance the pattern occurred randomly, meaning the clustering likely reflects something real, not just an artifact of where telescopes happen to look. Skeptics remain unconvinced by even this corrected number, arguing that with so few objects in the sample, statistical conclusions remain shaky no matter how carefully the math gets adjusted afterward. Add just one or two newly discovered objects to the mix, they argue, and the entire pattern could shift dramatically, potentially disappearing altogether. This disagreement is not settled, and it likely will not be settled through statistics alone, no matter how sophisticated the mathematics becomes on either side. Only one thing can truly end this scientific standoff for good, either directly detecting Planet 9 itself or discovering enough new objects to prove the clustering was never anything more than a trick of limited data all along. And in 2023, a newly discovered object would throw an unexpected wrench directly into the middle of this entire debate. To truly understand why observational bias worries scientists so deeply, imagine a simple experiment. Suppose you wanted to learn the average height of every person in a large city, but you only measured people walking past a single basketball court. Your sample would almost certainly skew taller than the city's true average, not because the city itself contains unusually tall people, but because basketball courts naturally attract taller players. Astronomical surveys face a strikingly similar problem. Telescope time is limited and expensive, so astronomers strategically choose which regions of sky to search based on practical factors that have nothing to do with where a hidden planet might actually be hiding. Weather conditions restrict certain months at certain observatories. The moon's brightness washes out faint objects during certain weeks of each month, forcing astronomers to work only during darker periods. Some regions of sky simply sit in better viewing position from a given telescope's location on Earth during certain seasons. All of these mundane, practical factors shape which small slices of sky actually get carefully searched, completely independent of where any hidden planet might genuinely exist. If, purely by coincidence, the well-searched patches of sky happen to overlap with where Sedna and its cousins were eventually found, the resulting cluster could look dramatically more significant than it actually is, an illusion created entirely by uneven searching, rather than by any real underlying gravitational cause. Correcting for this problem requires painstaking, detailed work. Astronomers must reconstruct, patch by patch, exactly how thoroughly every region of sky was searched across every survey ever conducted, then weight their statistical analysis accordingly, essentially asking, given exactly how hard we looked in each direction, how surprising is this pattern, really? This kind of correction work is slow, technical, and often thankless, the unglamorous side of astronomy that rarely makes headlines, but ultimately determines whether a flashy claim survives scientific scrutiny or quietly fades away under closer examination. For Planet 9, this corrective work has been performed multiple times by multiple independent research teams, and the results have consistently, if not overwhelmingly, favored the conclusion that real clustering exists beyond what bias alone could produce. That does not settle the debate completely. but it does mean the hypothesis has survived one of the harshest tests science can throw at any new idea. This is precisely how good science operates. Bold claims get challenged relentlessly from every possible angle. Ideas that survive sustained, rigorous attack earn increasing confidence over time. Ideas that collapse under scrutiny get discarded, no matter how exciting they originally seemed. Planet 9 has survived nearly a decade of this exact process. And then, in the summer of 2026, a single, newly confirmed object would test that survival more severely than anything that came before it. For years, every new discovery seemed to strengthen the Planet 9 case, each additional distant object falling neatly into the same clustered pattern that Batygin and Brown had first identified. Then, in 2023, Japanese astronomers using the Subaru telescope in Hawaii spotted a new object, later nicknamed Ammonite, officially designated 2023 KQ-14. At first, excitement built quickly. Ammonite belonged to the same rare category as Sedna, an object called a sednoid, extreme in its distance and its detachment from Neptune's gravitational influence. Only a handful of sednoids had ever been confirmed, making each new discovery precious and significant. But when researchers calculated Ammonite's full orbit, something did not fit. Instead of aligning neatly with Sedna, 2012 VP113, and the other clustered objects, Ammonite's orbit pointed in a noticeably different direction. It shared some broad similarities with the pattern, but not the tight alignment that had made the original clustering so statistically striking. Astronomer Yukun Huang, who studied the object closely, stated plainly that this new orbit lowered confidence in the original Planet 9 hypothesis. If a real planet were actively shepherding these distant worlds into alignment, every newly discovered sednoid should reinforce the same pattern. Ammonite did not. This moment illustrates something crucial about how real science actually works, messier and more honest than the clean, confident headlines usually suggest. A single new data point does not confirm a theory. It also does not necessarily destroy one. It complicates it, forcing scientists back to their models with an uncomfortable new piece of evidence that refuses to fit neatly into the existing picture. Researchers responded by exploring alternative explanations, rather than simply abandoning the hypothesis outright. One intriguing possibility suggests that a planet may have existed in this region once, actively shepherding these distant objects for millions of years, but was later ejected from the solar system entirely, flung out by a close gravitational encounter with one of the giant planets sometime in the ancient past. If that happened, the clustering among older, established objects like Sedna and 2012 VP113 could represent a kind of gravitational fossil, a lingering pattern frozen in place long after the planet, responsible for creating it, vanished into interstellar space. Meanwhile, newer discoveries like Ammonite, whose orbits may have shifted independently in the time since, would no longer perfectly match that ancient, frozen alignment. This ejected planet idea is elegant, but it remains speculative, one interpretation among several competing for the same increasingly complicated set of facts. What Ammonite proved, beyond any doubt, is that the picture is far more complex than early headlines suggested, and that complexity would only deepen further as astronomers turned toward an entirely different kind of evidence. One that did not rely on orbital clustering at all, but on something the hidden planet itself might be quietly radiating into space. Science does not run on convenient, tidy stories, no matter how satisfying those stories feel to tell. It runs on evidence, and sometimes evidence arrives that refuses to cooperate with the narrative everyone was hoping for. Ammonite's stubborn, misaligned orbit forces a deeper question worth sitting with. How much should a single outlier really matter? Statisticians face this exact dilemma constantly, across every field of science, not just astronomy. Imagine flipping a coin 10 times and getting 8 heads. That result feels suspicious. Maybe even like the coin is somehow weighted unfairly. Now imagine flipping it an 11th time and getting tails. Does that single extra flip completely erase your earlier suspicion? Not necessarily, but it should make you less certain than you were a moment before. Ammonite functions somewhat like that 11th coin flip. The original 6 objects that convinced Batyjin and Brown showed a striking, tight pattern. Ammonite does not perfectly fit that pattern. That single result alone cannot prove Planet 9 does not exist, but it meaningfully weakens the strength of the original claim, adding real uncertainty back into a picture that briefly looked settled. Some researchers argue Ammonite should be treated cautiously rather than as decisive proof against the hypothesis. Its orbit was only recently calculated, based on a relatively short window of observation. Small measurement uncertainties, especially for objects moving this slowly across the sky, can sometimes shift substantially once additional years of tracking data become available. It is entirely possible future observations will reveal Ammonite fits the pattern more closely than current calculations suggest. Other researchers take the opposite view, suggesting Ammonite represents exactly the kind of contradictory evidence that should make scientists seriously reconsider whether the original 6-object clustering was ever as significant as it first appeared, especially given how small that original sample size really was. This tension between competing interpretations is not a weakness in the scientific process. It is the process itself, working exactly as intended. Genuine uncertainty, openly debated, produces far more reliable long-term conclusions than false confidence rushed toward too quickly. What remains true, regardless of which interpretation eventually wins out, is this: orbital clustering alone, no matter how carefully studied, cannot settle the Planet 9 question on its own. Every argument built from clustering patterns depends on a relatively small handful of objects, each one adding enormous statistical weight, and each new discovery capable of shifting the entire picture dramatically in either direction. Astronomers needed something sturdier, evidence that did not depend entirely on comparing a handful of icy orbits against each other. They needed to search for the planet directly, and buried in old infrared data, collected by a spacecraft that had stopped operating years earlier, a completely different kind of search was quietly about to begin. There is a possibility more unsettling than Planet 9 simply hiding well. What if it is not hiding at all? What if it is gone, flung out of the solar system entirely, drifting alone through interstellar space where no telescope on Earth could ever hope to find it again? This idea sounds like science fiction, but the physics behind it is grounded in something astronomers understand quite well. During the solar system's chaotic youth, roughly 4.5 billion years ago, the giant planets were not sitting calmly in their current orbits. Jupiter, Saturn, Uranus, and Neptune drifted, migrated, and occasionally swapped positions entirely, a violent rearrangement scientists now refer to as planetary migration. During this turbulent period, close gravitational encounters between planets were common, and close encounters carry consequences. When two massive objects pass near each other, one often gets flung inward toward the Sun, while the other gets hurled outward, sometimes with enough force to escape the solar system's gravity entirely. If an early version of Planet 9 formed closer to the Sun, alongside Jupiter and Saturn, a violent encounter during this chaotic period could have kicked it outward with tremendous force, sending it either into a wide, distant orbit, the one we search for today, or possibly ejecting it from the solar system completely, sending it drifting alone into the emptiness between stars. This scenario would explain something that has puzzled researchers studying Ammonite's misaligned orbit. If Planet 9 actively shepherds nearby objects today, every newly discovered sednoid should show tight, consistent clustering. But if Planet 9 shaped these objects long ago, then vanished, the clustering we see now could be an old, frozen fingerprint, gradually blurring over billions of years, as smaller gravitational nudges from passing stars and background tides slowly scramble the original alignment. Objects like Sedna and 2012 VP 113, discovered earlier and matching the clustering closely, might represent the strongest, most preserved fingerprints. Ammonite, discovered later and less tightly aligned, might simply represent a slightly more scrambled remnant of that same ancient pattern. This ejected planet scenario carries a strange kind of poetry to it. Somewhere out there, drifting through the void between stars, an entire planet might exist completely alone, untethered from any sun, its surface locked in permanent, absolute darkness. Its only legacy, the faint gravitational echo it left behind on a handful of icy worlds, billions of miles from where it now travels. Scientists have a name for planets like this. They call them rogue planets, and remarkably, we already have strong evidence that such wandering worlds are common throughout our galaxy, drifting alone through the emptiness between star systems, visible to us only rarely, and only through the faintest gravitational hints they leave behind. If Planet 9 really was ejected long ago, it would join a surprisingly large, surprisingly strange population scattered throughout our galaxy. Astronomers estimate that rogue planets, worlds with no parent star at all, may actually outnumber every star in the Milky Way combined. This number sounds impossible until you understand how planetary systems actually form. When young stars are born inside dense, swirling clouds of gas and dust, dozens or even hundreds of planets can form simultaneously across a single, crowded stellar nursery. Gravity is not gentle during this process. Young planets collide, get flung into wildly unstable orbits, and frequently get ejected entirely by close encounters with larger neighbors, sent tumbling out into permanent darkness with no star to orbit ever again. Detecting these lone, starless worlds is extraordinarily difficult, since they emit no reflected starlight at all, no beacon for telescopes to latch onto. Astronomers have only managed to detect rogue planets through a rare and elegant technique called gravitational microlensing, where a rogue planet's gravity briefly bends and magnifies the light of a distant background star as it passes directly in front of it, creating a brief, telltale flicker in an otherwise steady point of light. If Planet 9 was ejected from our own solar system in its ancient past, it would now be one of these lone wanderers, drifting silently through interstellar space, its surface locked at a temperature barely above absolute zero. No sunrise, no sunset, nothing but permanent, unbroken night stretching across its entire surface for the rest of its existence. This theory carries a genuinely eerie implication. It suggests our solar system may have once hosted a ninth true planet, a world that formed alongside Jupiter and Saturn, weathered the same violent early chaos, and then simply vanished, erased from our neighborhood except for the faint gravitational fingerprint it left behind on a handful of small, icy worlds still orbiting billions of miles from the Sun. Not every scientist favors this dramatic explanation. Many still believe Planet 9 remains right where the original clustering evidence suggests, quietly orbiting far beyond Neptune, simply too faint and too far to have been photographed yet. The ejected planet theory remains one possibility among several, not a confirmed conclusion. But the very fact that serious scientists take this scenario seriously reveals something profound about how little we still understand regarding our own solar system's violent, chaotic youth. Whole planets may have formed and vanished before written history began, leaving nothing behind but scattered clues in the orbits of small, icy rocks drifting quietly at the edge of everything we know. And to test which version of this story is true, astronomers would need evidence stronger than orbital clustering alone, evidence that could only come from simulating the planet itself, then hunting for its faintest possible signal. How do you search for something you have never seen? You build it first, inside a computer, then hunt for the shadow it should cast across the real universe. This is precisely what Batygin, Brown, and dozens of other researchers have spent the past decade doing. Using powerful computer simulations, they create virtual solar systems, placing a hypothetical planet at a chosen mass, distance, and orbital tilt, then letting physics run forward across millions of simulated years, watching how that virtual planet's gravity would shape the paths of smaller, icier worlds nearby. Think of it like a detective building a suspect profile before ever seeing the suspect's face. Investigators study the clues left behind at a scene, then work backward to describe likely characteristics: height, build, behavior patterns. Simulations work the same way, using the clustering pattern in real Kuiper belt objects to work backward toward the specific properties a hidden planet would need in order to create that exact pattern. These simulations are not simple guesswork. Researchers test thousands of different combinations, adjusting mass, distance, and orbital tilt slightly each time, then comparing each simulated result against the real, observed clustering pattern. Combinations that fail to reproduce the pattern get discarded. Combinations that succeed get kept, gradually narrowing down an increasingly precise range of possible answers. Over successive rounds of refinement between 2016 and 2025, these predictions have grown steadily more specific. The original broad estimate suggested a planet somewhere between 5 and 20 times Earth's mass. Later refinements narrowed that range further, converging on a value closer to 6 or 7 times Earth's mass, orbiting at a somewhat closer distance than researchers originally proposed. This process illustrates something important about how modern astronomy actually operates. Long before any telescope directly photographs a new world, scientists often already possess a startlingly precise description of what that world should look like, built entirely through mathematics and physics rather than direct observation. It happened this way with Neptune. It appears to be happening again now, but a simulation, no matter how refined, remains a prediction rather than proof. Sooner or later, someone has to point an actual telescope at an actual patch of sky and either find the predicted object or fail to find it. For years, that direct search focused almost entirely on reflected sunlight, the same faint glow that reveals every other planet in our solar system. That approach kept coming up empty. Then, one small team of researchers tried something different entirely, hunting not for light reflected outward, but for warmth radiating from within. In 2006, Japan launched a modest space telescope named Akari, designed to survey the entire sky in infrared light, wavelengths invisible to human eyes, but rich with information about heat. For roughly 1 year, Akari quietly scanned nearly the entire sky, cataloging hundreds of thousands of infrared sources before its coolant ran dry and its most sensitive instruments went dark forever. For nearly 2 decades afterward, Akari's data sat largely untouched by the Planet 9 search, overshadowed by newer, flashier telescopes and more advanced surveys. Then a small international research team realized something everyone else had overlooked. Akari might hold the exact clue astronomers had been searching for the entire time, hiding quietly inside data collected years before anyone had even proposed Planet 9 existed. Here is the key insight that made Akari so valuable. Every search for Planet 9 up until this point had focused on reflected sunlight, the same faint glow astronomers use to spot every other planet in our solar system. But reflected light fades dramatically with distance, dropping off with the 4th power of that distance. Push an object twice as far away, and its reflected brightness plummets to 1/16 of its original value. Thermal radiation, the natural heat every object radiates simply by existing above absolute zero, behaves completely differently. It fades far more gently with distance, dropping off with only the square of that distance rather than the 4th power. Push an object twice as far away, and its thermal glow drops to just 1/4, not 1/16. At the staggering distances where Planet 9 likely orbits, this difference in physics becomes enormous. A planet essentially invisible in reflected sunlight could still shine, faintly but detectably, in infrared heat, provided the right telescope was sensitive enough to catch it, and Akari, during its brief working life, had conducted exactly the kind of ultra-sensitive infrared survey needed to potentially spot it. Researchers calculated Planet 9's expected temperature based on its predicted distance from the Sun, arriving at a frigid estimate somewhere between roughly -245 and -215 degrees Celsius, barely above absolute zero, the coldest temperature theoretically possible. Remarkably, objects at exactly this temperature emit their strongest infrared glow at wavelengths precisely matching Akari's most sensitive detection range. It was an elegant, almost poetic realization. A retired telescope, silent for nearly 2 decades, might still be quietly holding the answer to one of astronomy's greatest open questions, buried inside data nobody had thought to examine quite this carefully before. All that remained was searching through it, patiently, methodically, for a single faint object that should not be there. Searching Akari's archive data for Planet 9 required an almost absurd level of patience and precision. The team needed to filter through the telescope's full catalogue, eliminate every already known star, galaxy, and background object, then search whatever remained for one very specific kind of behavior, a faint object that stayed essentially frozen in place across a single day, yet drifted slowly across the sky when compared over the span of several months. That distinction matters enormously. Nearby objects, like asteroids close to Earth, streak visibly across the sky within hours. Distant background stars and galaxies appear permanently fixed, never budging no matter how long you observe them. An object at Planet 9's predicted distance would sit somewhere strange in between, essentially motionless minute to minute, yet unmistakably drifting when compared across months. Exactly the kind of subtle, patient motion a planet orbiting hundreds of times farther than Earth would display. After painstakingly filtering out cosmic rays, image artifacts, and thousands of already catalogued objects, the research team narrowed an enormous initial dataset down to a small handful of genuine candidates. Then, remarkably, 2 objects remained standing, both sitting within the theoretically predicted search region, both glowing with almost exactly the infrared brightness that a Planet 9-sized world should produce at that specific distance. Researchers were careful, appropriately, not to declare victory. 2 candidates is not confirmation. It is a lead, an intriguing, carefully qualified lead, but a lead nonetheless, the strongest one the decades-long search had produced up to that point. A separate but related research effort took a slightly different approach, comparing Akari's newer data against an even older infrared survey called IRAS, launched all the way back in 1983. By comparing object positions across a full 23-year gap between these 2 surveys, researchers could measure motion with far greater precision than a single survey alone would allow. This comparison produced its own standout candidate, one whose measured shift between the 2 surveys matched almost exactly what a slow-moving object at roughly 500 to 700 times Earth's distance should display. Its estimated temperature and its estimated mass both fell remarkably close to the range Batygin and Brown had originally predicted back in 2016. None of these candidates constitute proof. Each one requires urgent, careful follow-up observation, using dramatically more powerful modern telescopes capable of confirming whether these faint infrared points are truly moving the way a real, distant planet should move, or whether they are simply cosmic imposters, chance alignments of background noise that happen to land in exactly the right place at exactly the right time. It seems almost contradictory. A planet so far from the sun that daylight there would look like a faint star in a black sky, a world locked at a temperature barely above absolute zero, and yet it still glows, faintly, steadily, in a very specific kind of light our eyes were never built to see. The explanation lies in a basic law of physics that governs literally everything in the universe with a temperature above absolute zero. Every object, whether it is a star, a planet, a person, or even a block of ice sitting in a freezer, constantly radiates energy outward in the form of heat. Hotter objects radiate more intensely and at shorter wavelengths, which is why something extremely hot, like the filament inside an old-fashioned light bulb, glows visibly bright to human eyes. Colder objects radiate far more weakly and at much longer wavelengths that stretch beyond what human eyes can detect, but which specialized infrared telescopes can capture perfectly. A planet like Earth, sitting comfortably warm from nearby sunlight, radiates most of its heat in infrared wavelengths too faint and too long for human eyes to notice directly, though we can feel it as warmth radiating off pavement on a hot day. Planet 9, sitting almost unimaginably far from any warming sunlight, would radiate its own leftover internal heat instead, a faint afterglow left over from its original formation billions of years ago, slowly leaking out into space as the planet gradually cools across unimaginable stretches of time. This leftover internal heat, sometimes called primordial heat, offers a genuinely elegant solution to an incredibly difficult detection problem. Even a planet receiving essentially no meaningful warmth from the distant sun still carries enormous residual heat trapped inside from its original violent formation, heat that continues radiating outward into space for billions of years afterward, slowly, steadily, detectably. Jupiter itself demonstrates this exact same principle right here in our own solar system. Jupiter actually radiates roughly twice as much energy back into space as it receives from the Sun, energy left over from its own ancient formation, still slowly leaking outward even today, billions of years after the planet first came together. If Planet 9 formed the same way other giant planets did, through the same violent, energetic process of gas and ice collapsing together under gravity's pull, it should carry a similar reservoir of leftover internal heat, faint but real, and crucially, detectable by exactly the kind of sensitive infrared telescope that Akari happened to be. This is precisely why the infrared search strategy represents such a genuinely clever breakthrough. It does not require Planet 9 to reflect meaningful sunlight at all, sunlight that would be almost impossibly faint at these extreme distances. It only requires the planet to still be cooling down from its own ancient birth, a process every giant planet undergoes, and one that continues, quietly, for billions of years after formation. Numbers alone rarely mean much without something familiar to measure them against. So picture this instead. Stack 10 Earths together into a single planet, and you arrive somewhere near the upper range of what scientists currently expect Planet 9's mass to be. That comparison alone probably does not fully capture the scale involved, so try another angle. Earth itself already dwarfs everything humans have ever built or experienced directly. Our planet measures roughly 8,000 miles across, wide enough that a commercial jet flying non-stop would need well over a full day just to circle it once. Planet 9, at an estimated 5 to 10 times Earth's mass, would likely measure several times wider than Earth as well, closer in overall size to Neptune or Uranus than to our own rocky home. To put this in perspective, using something closer to everyday experience, imagine Earth shrunk down to the size of a basketball. On that same scale, Planet 9 would likely be roughly the size of a large beach ball, several times bigger, several times heavier, an entirely different class of world compared to the rocky planets close to the Sun. This size places Planet 9 into a fascinating and increasingly important category that astronomers call sub-Neptunes, planets smaller than ice giants like Neptune and Uranus, but dramatically larger and heavier than rocky worlds like Earth or Mars. Remarkably, sub-Neptunes appear to be one of the single most common types of planet found orbiting other distant stars throughout our galaxy, based on extensive data gathered by planet-hunting space telescopes over the past 2 decades. That statistic carries a strange and slightly humbling implication. If Planet 9 truly exists, our solar system may finally possess one of the most common planet types found throughout the entire galaxy, a category we had somehow completely missed hiding in our own cosmic backyard the entire time. Composition remains uncertain, though scientists have reasonable expectations based on where and when this hypothetical planet likely formed. Most models suggest Planet 9 probably contains a thick, dense atmosphere composed largely of hydrogen and helium, surrounding a deeper, heavier core made of ice, rock, and various frozen compounds, broadly similar in overall structure to Neptune and Uranus, just considerably smaller in overall scale. If confirmed, Planet 9 would not simply represent one more addition to our solar system's roster. It would represent an entirely new category of world for our neighborhood, one we already understand exists commonly throughout the wider galaxy, yet somehow overlooked directly at home for centuries, hiding in plain sight simply because it orbits so unbelievably far from everything else we already know. Stand on the surface of Planet 9, if such a surface even exists beneath its thick atmosphere, and look up toward the sun. You would not find a bright disk warming your face the way it does on Earth. You would find something closer to an unusually bright star, distinguishable from the thousands of other stars scattered across the sky only by its slightly larger size and its faint, steady glow. At roughly 700 times Earth's distance from the sun, sunlight arriving at Planet 9 would carry only a tiny fraction of the warmth and brightness we experience here. Using the same inverse square rule that governs light everywhere in the universe, sunlight at this distance would be roughly 500,000 times fainter than what reaches Earth. Noon on Planet 9 would look less like daylight and more like a deep, permanent twilight, dim enough that human eyes would need real time to adjust before making out any details at all. Temperature tells an even more extreme story. Scientists estimate Planet 9's surface, or whatever passes for one beneath its thick atmosphere, sits somewhere between roughly -245 and -215 degrees Celsius. For comparison, the coldest naturally recorded temperature ever measured on Earth, deep in Antarctica, reached only about -90 degrees Celsius. Planet 9 would be colder than that by more than 150 additional degrees, closer to the absolute physical limit of cold that the universe allows. At these temperatures, familiar materials behave in deeply unfamiliar ways. Substances that exist as gases here on Earth, like nitrogen and oxygen, would freeze solid, potentially forming strange, exotic ices layered across the planet's deeper regions. Water, if present at all, would exist only as rock-hard ice, harder and more rigid than granite. One full orbit around the Sun, one single Planet 9 year, would take somewhere between 10 and 20,000 Earth years to complete. Consider what that actually means. If Planet 9 existed, and someone had been watching it since the invention of writing roughly 5,000 years ago, that observer would have witnessed barely 1/4 of a single orbit complete, a journey so slow it makes all of recorded human civilization look like a brief passing moment. No spacecraft humans have ever built could realistically reach such a world within a single human lifetime using current propulsion technology. Voyager 1, humanity's most distant spacecraft, launched in 1977, and still has not traveled far enough to reach Planet 9's predicted minimum distance, even after nearly 5 decades of continuous travel through space. Planet 9, if it exists, represents something genuinely rare in our solar system, a true frontier world, sitting at the absolute edge of what gravity still meaningfully connects to our sun, drifting through darkness and cold so extreme it barely resembles anything found anywhere closer to home. High in the mountains of northern Chile, at an altitude where the air grows thin and the night sky turns impossibly clear, a new observatory has begun its work. Named after astronomer Vera Rubin, whose research helped reveal the existence of dark matter decades ago, this facility now carries humanity's best realistic chance yet of finally settling the Planet 9 question once and for all. The Vera Rubin Observatory houses something genuinely unprecedented, a camera roughly the size of a small car, capable of capturing images at 3.2 billion pixels per photograph. the largest digital camera ever constructed for astronomical use. To put that number into perspective, you would need hundreds of standard high-definition televisions arranged together just to display one single, full-resolution image. This camera produces in a single shot. This telescope's primary mission carries an equally massive name: the Legacy Survey of Space and Time. Over 10 full years, it will repeatedly photograph nearly the entire visible southern sky, creating what scientists describe as a continuous, decade-spanning movie of the heavens, capturing every visible change, every flicker, every faint object drifting slowly across the darkness. For Planet 9 specifically, this repeated, systematic coverage solves the single biggest obstacle that has frustrated searches for an entire decade. Previous telescopes could only examine small patches of predicted sky at any given time, forced to guess which specific region might be worth the enormous time investment required. Rubin instead photographs enormous swaths of sky automatically, every single clear night, gradually building up complete, thorough coverage of the entire predicted search region without needing to guess correctly in advance. The technical process powering this search relies on something astronomers call difference imaging. Software automatically compares each new photograph against a carefully built template constructed from previous observations of that exact same patch of sky. Anything that has moved, brightened, or changed in any way between images triggers an automatic alert, flagging it for further investigation. During its earliest testing phase in early 2026, this system generated over 800,000 such alerts within a single night alone. Mike Brown himself, the very astronomer who first helped propose Planet 9's existence back in 2016, has expressed genuine excitement about what Rubin might reveal. He has noted that even a negative result, a thorough, confirmed absence of any matching object across the entire predicted search region, would represent a genuinely important scientific outcome, finally closing the book on a full decade of dedicated searching. For the first time since Batygin and Brown's original prediction, astronomers now possess a telescope genuinely capable of conducting the kind of complete, systematic search this mystery has always demanded. The wait, after 10 long years of frustrating uncertainty, may finally be approaching its end. To understand exactly why the Vera Rubin Observatory represents such a genuine turning point, compare it directly against the painstaking, frustrating searches that came before it. Traditional planet-hunting telescopes typically focus on one small patch of sky at a time, capturing detailed images, then manually or semi-automatically comparing them against earlier photographs of that same tiny region, hunting for anything that might have moved. This process works reasonably well for searching small, carefully targeted areas. But Planet 9's predicted location covers an enormous stretch of sky, far larger than any single telescope. Using this older, patch-by-patch method could realistically cover within a reasonable amount of time. Rubin solves this fundamental problem through sheer, overwhelming scale. Its massive camera can photograph an area of sky roughly 40 times larger than the full moon in a single exposure, then move to the next adjacent patch within seconds, repeating this process continuously throughout every single clear night. Across its planned 10-year survey, Rubin will photograph the same regions of southern sky hundreds of separate times, building layer upon layer of data capable of detecting even the faintest, slowest moving objects imaginable. This approach transforms the entire search strategy. Instead of astronomers carefully selecting one small target region and hoping it happens to be correct, Rubin essentially photographs everything, then lets sophisticated software sort through the results afterward, flagging anything unusual for follow-up investigation by human researchers. For an object moving as slowly as Planet 9 likely does, drifting perhaps just a few arc-seconds across the sky per year, detecting genuine motion requires exactly this kind of patient, repeated observations stretched across a long period of time. A single photograph could never reveal such subtle motion. Dozens, or even hundreds of photographs, captured methodically across months and years, absolutely could. Rubin's approach also solves another persistent headache that plagued earlier, smaller-scale searches. The problem of false positives, cosmic rays striking camera sensors, distant background galaxies, and countless other sources of visual noise can easily mimic the appearance of a genuine moving object in any single image. But an object that appears to move consistently, smoothly, and predictably across dozens of separate images taken over months becomes vastly more difficult to dismiss as mere coincidence or sensor error. Scientists studying the outer solar system described this moment as something close to a genuine turning point in the search. Not necessarily a guarantee of success, but finally, after a full decade of frustration and uncertainty, a realistic, credible chance of either confirming Planet Nine's existence directly or definitively ruling it out across its full, predicted range of possible locations. Every scientific mystery eventually reaches a moment where speculation gives way to direct evidence, where careful mathematics and clever inference finally meet the blunt, undeniable proof of direct observation. For Planet 9, that moment may finally be approaching. The Vera Rubin Observatory began its formal 10-year survey in the summer of 2026, and astronomers who have spent their entire careers chasing this mystery are watching with a mixture of genuine excitement and carefully managed expectation. Megan Schwamb, a planetary scientist who has closely studied the outer solar system for years, has indicated that if Planet 9 truly exists within its primary predicted search region, Rubin stands a strong realistic chance of identifying it within the survey's opening years, rather than requiring the full decade to complete its work. This timeline matters enormously, not just for scientific curiosity, but for an entire generation of researchers who have built their careers around this specific question. Some astronomers have spent 20 years or more directly involved in this search, refining predictions, building simulations, developing entirely new detection strategies, all in pursuit of a single, elusive answer that has remained frustratingly out of reach since Batygin and Brown's original 2016 prediction first captured the world's imagination. If Rubin succeeds in directly detecting Planet 9, the discovery would immediately validate an entire decade of careful theoretical work, transforming a widely debated hypothesis into a confirmed, celebrated scientific fact almost overnight. It would also finally resolve the tensions surrounding objects like Ammonite, whose slightly misaligned orbit had complicated the clustering evidence so significantly just months earlier. But scientists are also carefully preparing themselves for an entirely different, less dramatic possible outcome. If Rubin thoroughly searches the full predicted region and finds absolutely nothing matching Planet 9's expected characteristics, that negative result would itself carry enormous scientific weight, forcing researchers back to their models, back to their assumptions, and potentially back toward alternative explanations for the clustering that started this entire decade-long mystery in the first place. Either outcome would represent genuine, meaningful scientific progress. Confirmation would rank among the most significant astronomical discoveries in well over a century, expanding our solar system's family for the first time since Pluto's discovery back in 1930. A confirmed absence would force scientists to seriously reconsider decades of assumptions about how our solar system's most distant, mysterious region actually formed and evolved. What makes this particular moment in astronomical history so genuinely compelling is the palpable sense of anticipation surrounding it. For the first time in this entire decade-long search, astronomers finally possess a tool capable of delivering something resembling a definitive answer, rather than simply adding one more data point to an already lengthy, ongoing debate. Confirming Planet 9's existence would reshape far more than just textbooks and classroom diagrams. It would fundamentally reshape how scientists think about navigating and understanding the outer solar system, including any future missions that might eventually attempt to explore this distant, largely unmapped frontier. Consider first the practical challenge of actually reaching such a world. Voyager 1, launched in 1977 and still transmitting data back to Earth after nearly 5 decades of continuous travel, has journeyed farther from the Sun than any human-made object in history. Yet, even after this extraordinary, unprecedented journey, Voyager 1 still has not traveled far enough to reach Planet 9's predicted minimum distance from the Sun. Any realistic future mission specifically targeting Planet 9 would require entirely new propulsion technology. Spacecraft capable of traveling dramatically faster than anything currently available, simply to reach this distant target within a reasonable human timeframe rather than requiring multiple centuries of travel time. Beyond the challenge of physically reaching such a distant world, Planet 9's gravity would also meaningfully reshape how scientists calculate and predict the paths of other objects throughout the outer solar system. Every spacecraft trajectory, every calculated orbit for a distant comet or asteroid would need to formally account for this newly confirmed planet's gravitational influence, adding an entirely new variable into calculations that astronomers have relied upon for generations. This is not simply a technical curiosity confined to specialist researchers. Long-term trajectory planning for any future deep space missions exploring the outer solar system would need to factor in Planet 9's gravity precisely, particularly for any spacecraft attempting close, extended encounters with the various icy worlds scattered throughout that same distant, remote region. There is also a broader, more philosophical implication worth sitting with here. Confirming Planet 9 would prove definitively that our solar system remains genuinely, meaningfully incomplete in our current understanding, even after centuries of dedicated observation and mapping. If an entire planet, several times more massive than Earth itself, has managed to remain completely hidden from view this entire time, simply by orbiting far enough away, it raises an uncomfortable and genuinely fascinating question about what else might still be waiting out there, quietly hidden in the vast darkness beyond Neptune, patiently waiting for humanity's telescopes to finally grow powerful enough to notice. Here is a question that unsettles even scientists who fully support the Planet 9 hypothesis. If one massive, previously unknown planet can hide successfully for this long, what stops a second one from doing exactly the same thing, drifting quietly somewhere even farther out in the darkness? This is not idle, baseless speculation. Some researchers studying the detailed clustering patterns among distant Kuiper belt objects have noticed subtle irregularities that a single planet, even one as massive as Planet 9's predicted upper range, cannot fully and cleanly explain on its own. A handful of studies have proposed that two separate planets, rather than just one, might together produce an even better, more precise match to the observed clustering pattern than any single planet model manages to achieve alone. If true, this would mean our solar system's outer reaches are considerably more crowded and more complex than even the boldest current headlines already suggest, containing not one, but potentially two entirely unknown massive worlds, both quietly orbiting far beyond Neptune's familiar, well-mapped territory. Scientists remain understandably cautious about this particular idea. Adding a second hypothetical planet into an already complicated model introduces significant additional complexity, and good science generally favors the simplest possible explanation that still successfully accounts for all the observed evidence. A principle researchers often call Occam's razor. Two unconfirmed planets require considerably stronger evidence to justify than one. Still, the outer solar system has already surprised scientists dramatically and repeatedly throughout the past several decades. Few researchers seriously expected Sedna's existence before its unexpected discovery back in 2003. Even fewer expected the tightly clustered pattern that followed in the years afterward. Given this established track record of persistent surprises, few astronomers are willing to completely rule out the genuine possibility of additional hidden worlds still waiting patiently to be found. If the Vera Rubin Observatory successfully confirms Planet 9's existence in the coming years, the very next question on every astronomer's mind will almost certainly become obvious. Are there more? Is Planet 9 merely the first hidden world we finally managed to detect, rather than the only one quietly lurking out there in the darkness? For now, This remains firmly in the realm of careful speculation rather than established, confirmed science. But it serves as a genuinely powerful reminder of just how much of our own solar system likely remains completely unknown and unexplored, even today, even after literally centuries of dedicated telescopic observation by generations of careful, patient astronomers. Step back for a moment and consider the full, sweeping arc of this entire story. For most of recorded human history, people confidently believed the solar system contained exactly 6 planets, the only ones visible directly to the naked human eye. Then telescopes revealed Uranus. Then careful mathematics revealed Neptune. Then a fortunate accident revealed Pluto, later demoted once astronomers fully understood its true, much smaller size and nature. Each and every one of these historic discoveries fundamentally reshaped how humanity understood our cosmic neighborhood, and each single discovery arrived only after we had already convinced ourselves the map was essentially finished, essentially complete. Planet 9 represents the latest chapter in this same repeating, humbling pattern. For decades, our understanding of the solar system's outer edge felt relatively settled and secure, extending confidently out to Neptune's orbit, with the Kuiper belt serving as a scattered, sparse afterthought trailing quietly behind it. Sedna's unexpected discovery in 2003 shattered that comfortable assumption completely, revealing an entirely new region of unexplained structure and mystery that nobody had previously anticipated. What makes this pattern genuinely uncomfortable, in the best and most productive scientific sense, is how consistently it keeps repeating throughout history. Each single generation of astronomers has confidently assumed they finally possessed a complete, accurate picture of our solar system. Each and every generation, without exception, turned out to be wrong in some genuinely significant way. This history offers an important and humbling lesson that extends well beyond this single specific mystery. Our solar system, the literal cosmic neighborhood we call home, remains genuinely, meaningfully unmapped at its most distant edges, even in an era of remarkably powerful modern telescopes and advanced technology. Entire planets, if Planet 9 or a similar undiscovered world genuinely exists, can successfully hide from direct human detection for centuries, simply by orbiting far enough away from the sun's revealing light. Modern tools like the Vera Rubin Observatory represent our very best realistic chance, yet at finally closing this persistent, recurring gap in our collective cosmic knowledge. But even if Rubin successfully confirms Planet 9's existence once and for all, history strongly suggests we should not assume the map is finally, truly complete. Something else, somewhere out there in the vast surrounding darkness, is very likely still waiting patiently to be found, exactly the way Planet 9 itself waited patiently for over a full century before anyone even thought to seriously look for it. Imagine, for a moment, the exact instant this discovery becomes fully and officially confirmed. Somewhere at the Vera Rubin Observatory, or perhaps at another powerful telescope conducting careful, dedicated follow-up observations, a faint point of light finally, unmistakably confirms its slow, steady motion across the deep, star-filled sky, moving exactly the way Planet 9 has always been predicted to move. The immediate, tangible impact would be nothing short of enormous. School textbooks around the entire world would require official updates for the first time since Pluto's controversial demotion back in 2006. Planetariums would need to redesign and rebuild their scale models of our solar system to properly account for this newly confirmed member. An entire generation of students would grow up learning about 9 confirmed planets once again, though this new 9th world would look absolutely nothing like the small, icy, distant Pluto that originally held that same numbered position for the better part of a century. Beyond the purely educational and cultural impact, the scientific implications would run considerably deeper and more significant. Confirmation would validate an entire, sophisticated methodology, careful mathematical prediction, based purely on subtle gravitational effects, succeeding brilliantly for the second time in less than 2 centuries of scientific history. It would meaningfully strengthen our fundamental confidence in using similar indirect methods to search for other undiscovered worlds, both within our own solar system and around other distant stars scattered throughout the wider galaxy. The discovery would also fundamentally transform our broader understanding of exactly how planetary systems form and evolve over time. Currently, sub-Neptune-sized planets, the same general size category Planet 9 likely belongs to, rank among the single most common types of planet found throughout our entire galaxy. Yet our own solar system had always appeared to be conspicuously missing this common category entirely. Confirming Planet 9 would finally resolve that nagging inconsistency, revealing our own solar system to be considerably less unusual and considerably more typical than scientists had previously assumed. There is a certain deep irony worth sitting with here as well. Michael Brown, the very same astronomer whose earlier discoveries helped strip Pluto of its official planetary status, would become the very same scientist most closely associated with confirming an entirely new, genuine planet to take its place in our solar system's official lineup. Perhaps most significantly of all, this discovery would powerfully reaffirm something that runs far deeper than any single planet, however massive or however far away it might be. It would prove, once again, that mathematics and careful, patient human curiosity remain fully capable of revealing entire hidden worlds, long before we ever manage to actually see them directly with our own eyes. Every single thread woven throughout this entire story now converges on one single, defining moment. Sedna's lonely, impossible orbit, discovered by pure accident over 2 decades ago. The eerie, unmistakable clustering among 6 separate, independently discovered icy worlds. Batygin and Brown's bold, carefully calculated 2016 prediction. Ammonite's stubborn, complicating orbit that refused to fit the tidy expected pattern. 2 faint, tantalizing heat signatures quietly captured by a retired Japanese telescope decades after its original mission had already ended. And now, finally, the largest, most powerful camera ever constructed for astronomical use, systematically scanning the entire predicted search region, night after night, patiently building toward an answer. This moment did not arrive suddenly or without warning. It was assembled patiently, piece by careful piece, across more than 2 full decades of dedicated observation, rigorous mathematics, heated scientific disagreement, and the quiet, patient persistence of researchers who refuse to simply let this particular mystery go unresolved. What makes this specific moment in astronomical history feel genuinely different from everything that came before it is the sheer convergence of independent evidence now pointing in roughly the same general direction. Orbital clustering among distant Kuiper belt objects, a conspicuous, unexplained gap in the Kuiper belt's population, faint but real infrared heat signatures matching precise theoretical predictions, and now an entirely new, purpose-built telescope, finally capable of conducting the complete, systematic search this exact question has always genuinely demanded. No single piece of this accumulated evidence, taken entirely on its own, proves anything definitively, but taken together, considered carefully as one unified whole, they paint an increasingly compelling picture of something massive, something real, quietly orbiting in the vast darkness beyond Neptune, patiently waiting for our technology to finally catch up with our own careful, persistent mathematics. Within the coming months and years, the Vera Rubin Observatory's ongoing survey will very likely deliver the single most important scientific update to this entire decade-long story. Either a confirmed, undeniable direct detection, finally proving Planet 9 genuinely real after everything, or a thoroughly confirmed absence across the full predicted search region, forcing scientists to seriously reconsider decades of careful, accumulated assumptions. Whatever the ultimate final answer turns out to be, one thing has already become absolutely, undeniably clear throughout this entire journey. Our solar system, the same cosmic neighborhood humans have studied, mapped, and confidently claimed to fully understand for literally centuries, still holds genuine, meaningful secrets. Something out there, at the absolute edge of everything we currently know and understand, continues quietly shaping the paths of smaller worlds nearby. We are closer than we have ever been before to finally learning exactly what that something actually is.